Hi, and welcome to this demonstrations of benefits of running ECM containers on Kubernetes Docker orchestration platform. In this demonstration, I will show you how to quickly deploy ECM content platform services onto this Kubernetes platform, as well as deploy Content Navigator. I'll also demonstrate the built-in feature and capabilities that you will benefit from running ECM containers on a Kubernetes orchestration platform. Some of these features include resiliencies, faster upgrading and patching of ECM containers, as well as being able to dynamic auto scale based on your workload. For my Kubernetes platform, I have chosen IBM Cloud Private as my Kubernetes orchestration platform. On this platform, I have one master node, one proxy node, one management node, and 3 worker nodes. If we go over to take a look at the deployment, I currently do not have any ECM applications that are currently deployed. In order for me to deploy an ECM container or an application onto a Kubernetes orchestration platform, I need to create a deployment YAML file that describes how I want to deploy the ECM containers. In this case, I have a deployment YAML file for CPE. And there are a couple characteristics in this deployment YAML file that I want to point out. The first item is the number of replicas. The number of replicas defined how many Kubernetes containers or pods that I want to deploy for my CPE applications. In this case, I have defined 2 in order to provide high availability and load balancing. The other thing also is I define a pod anti-affinity. This ensures that my 2 containers or pods that I deploy in Kubernetes are not deployed on the same worker node for better resiliencies. The other aspect in here is the image name that I want to use to deploy for my CPE container. Lastly, there are 2 other capabilities I want to point out that will help improve running ECM containers in Kubernetes. The first is the Readiness Probe. The Readiness Probe tells Kubernetes when the container is fully up and running in order before it routes traffic to the containers. This will ensure that client traffics are not routed to containers before it's fully up and running. The last capability is the Liveness Probe. The Liveness Probe tells Kubernetes how to check whether or not the containers or pods are in a healthy state. If it detects that the Liveness Probe has failed, it will automatically terminate and kill and reinstantiate the container so that it goes back into a healthy state. Now that I have defined my deployment descriptor, I simply deploy my containers by running a single kubectl command or Kubernetes CLI command. In this case, it's kubectl create-f, and I will source the deployment YAML file that I just described. If you compare this to traditional on-prem, you'll notice that traditionally installing and deploying CPE on-premise with traditional WAS, for example, will take potentially hours or several hours before you can get it up and running. But if here, I just finished executing the command and the deployment of CPE has started. If we take a closer look at the deployment, you'll realize and notice some of the characteristics that I did point out in the deployment YAML file. The first thing is I had defined 2 replicas, and there are now 2 containers or pods that are deployed within the Kubernetes cluster. I've also defined pod anti-affinity to ensure that each of my containers are running on separate hosts or the Kubernetes cluster nodes. You'll notice here that the host IP are 2 different IPs. Lastly, if we take a look at one of the pods and containers, you'll show it's being starting up, and eventually you'll notice that the Readiness Probe will start to kick in. Let's go take a look at the other pod to see if the Readiness Probe has started for that one. Nope, not yet. So while that is going, I will also go ahead and deploy my CN container. Again, I will use the same kubectl command with create, and I will source the deployment YAML file. Okay, that has now created. Oh, and as you notice here, the readiness is now 1 of 1, which tells me that the readiness probe has succeeded. I should now be able to access my CPE application through the services load balancer that I had already created. It takes a little bit for the first time when you access CPE ACE for the applications to ramp up initially. While that is being accessed, let's go take a look at our ICN applications. And you notice here that the ICN application has also started. One of the containers is in a ready state. Okay, so as you can see here, I have logged into ACE, and I have one object store that I've already created. And let me log out of here, and I will go ahead and launch the navigator. All right, as you can see here, it didn't take me very long to deploy both CPE and ICN, and I was able to log in and access. All right, so the next thing I want to demonstrate is the resiliency aspect of running on Kubernetes orchestration platform. So if I take a look at what is actually running on my worker node 1, I do a docker ps-a, and I grep for CPE. Let me see if I can find a CPE container. I do have a CPE container. And let's go back into the deployment YAML file, or say the dashboard. And if we take a look, you'll notice that the container is running on worker node 1. What I will do is I will go ahead and kill this worker node, and we'll see what happens. Okay, I killed that worker or that CPE container. If I check for the CPE container again, guess what? The container that I killed has exited, but you'll notice is that there's a new container that had respawned automatically. And the reason for this is that on every single Kubernetes node, there's a kubelet process that watches what containers are actually running on the worker nodes. And if it detects that that container has died or has been killed, it will automatically respawn a corresponding container to replace it. So this is one of the built-in capabilities that you get with Kubernetes orchestration platform to ensure application resiliencies that you normally would not get with traditional on-prem software. The next thing I want to demonstrate is the ability to do online upgrading and patching with zero impact. So if we take a look at my ICN upgrade deployment YAML file, again, the deployment YAML file is pretty much similar. The only thing that I've changed is the rolling update behavior. I have a max search of 1 and max unavailable of 1. This ensures that there's always one container of the previous version is always up and running to ensure that there's zero impact to their end users. The only other thing that changes is the image that I'm going to deploy. If you notice here, I have a new image name or a new image tag ID that I'm going to deploy compared to the previous one. Let me go back to the previous ICN. This is our GM candidate, and I'm going to replace it with 303 interim fix 3. So, just for the sake of knowing exactly what we have, I'm going to go to the Navigator ping page. And here is the version that I'm currently running. So now I'm going to replace it with 303 interim fix 3. And again, all I need to do is run a kubectl command to update my existing deployment. This time I'm going to do a replace, and I'm going to specify my upgrade deployment YAML file. Okay, it has initiated. If we go back to the deployment, you'll notice that the ICN container has changed. Remember my rolling update characteristic it had indicated that I want to make sure that I have one original Navigator container running the old build always up and running so that I have no impact to my existing users as it starts up 2 of the new containers of the new image. While that is going, I will put into another browser so that way we leave the ping page for ICN intact, and I will go ahead and access Navigator. Let me log in. I'm able to log in. Now let's go back and check how the rolling update is occurring. Oh, it looks like one of the container is up and running. So let me go do the ping page and compare what we used to have and what we're currently running now. As you notice, the previous version was our 303 GA build, and what we're running now is 303 interim fix 3. You notice that it didn't take very long to do a patching or upgrade to a new version of Navigator. If I wanted to roll back, all I have to do is update my deployment YAML file and point it back to the original Docker container image for Navigator. So lastly, what I'm going to demonstrate is the dynamic auto-scaling capability of Kubernetes. So currently, right now, I have no scaling policies that I have defined. In order for me to define a scaling policy, again, all I need to do is create a YAML file that defines my scaling policy that I want to create for Navigator. In my case, What I wanted to do is, I already know that I have a minimum replicas of 2, and I want to be able to scale out to 3. And then I want to be able to specify the metrics for what I want to do for scaling that would trigger an auto scaling, which is CPU. And in order for me to ensure that I'm going to trigger it, I'm going to set it to 20%. For me to create the scaling policy, again, is a simple kubectl command, create-f. And again, you'll see here that I have created an auto-scaling policy. So let me go ahead and trigger an auto-scale by accessing Navigator. Let me go back over here to put some additional workload. Okay. As you can see here, the auto scale has triggered. It says new size is 3. If I go over to my deployment, there should be 3 that is going to be active. And the nice thing about the auto scaling is that not only will it scale out, it will also scale in. If I leave it idle for a certain period of time, it will automatically scale back in. That is the last demonstrations for the benefits of running ECM containers on a Kubernetes orchestration platform. I hope you found this demonstration useful and of value for you. Stay tuned for the next demo.